All right, so here is a circuit diagram. I want to walk through like the whole process of getting the. We start with the circuit diagram, then we're going to get a logic expression for it, unsimplified. Then we're going to simplify it. Then we're going to build the simplified circuit. There's two different circuits I want to show you. The first one is to illustrate what happens when we do inverters after we've done like AND or OR gates. And then the second circuit is one that we're going to simplify and then build the circuit in Tinkercad. So let's start with just this circuit so I can show you what happens. So right here, we're gonna follow this circuit through to get the logic statement. So we got X coming over here. Once we go through the inverter, we have not X. And then right here, we've got Y. So then with the AND gate, coming out of the AND gate would be not X and Y. Then that is going to go through an inverter. So that means that we're going to have the same thing that we had before, but with an inverter line over all of it. Also, be really careful. As a little aside note here, if you're doing something like this, or let me change letters there. Let's say you're going to do something like this. You've got not X, and you've got, dang it, I didn't want to use X and Y. You've got not A. What have you got? Yeah, not A and not B as inputs to an AND gate. Be very careful. This comes out as not A and not B. Be really careful you don't connect that line up there because it's different. Not A and not B is really different from not A and B. Because if you remember the theorem, not if it's over both of them, we break that apart, it's not A or not B. So totally different having the line connected and having the line separated. So if you have two negated things going in there, they each have their own little thing on top. If you had this, not A and B, would mean you had A and B going into an AND gate, then you would have A and B coming out. Then if you went through the inverter, then you would have not A and B. So that is different from not A and not B. Does that make sense? I hope it does. I'll leave this here for a minute and then I'll erase it when I need the room. Okay, back to this circuit. So we have not X and Y. Down here we've got X and then we've got Y. Goes through an inverter to be not Y. Then they go through an OR gate. So we have X or not Y. And now that chunk is going to go through this inverter, which means on the other side, we're going to have X or not Y with a negation over the whole thing. And then this final OR gate gives us not X and Y or not X or not Y. Okay, so the big point there was the difference between having an inverter over like a group of things versus two inverted things getting grouped together. They have different meanings. Because if you have one line over the top of them, we can do this theorem. If we don't, then we can't. So let me go through simplifying this expression with you. Okay, so we're going to simplify this expression. All right, so the first thing I'm going to do is I'm going to use theorem 20 and 21. The De Morgan's theorems, I have 20 that's going to break apart the multiplication and 21 that's going to break apart the addition. So I'm going to use theorems 20 and 21 to break apart this one. So if I break this, it'll have a plus in between. Break the line, change the sign, and so we have not x here and y there. Then if I break this one, it's going to be not x and not y. Break the line, change the sign, right? So now I have a couple of, I have not x, which is x, and I have not y, which is y. And that is theorem number 9. Not x is x. So we're going to use theorem number 9 twice. To say not x is x. So now we have x or not y or not x and y. And now if you look at the last two terms, we have the consensus theorem. Remember, it's the buddy theorem. If you have two opposites with a plus sign in between them, and one of them has a buddy, the one with the buddy goes away. So we're going to use the consensus theorem and see if we can figure out which version of it we have. We have a y and a not y. The one with the buddy doesn't have a negation, but its buddy does. So the buddy doesn't have a negation, but the buddy does. So the buddy doesn't have a negation. Wait, which one were we at? But its friend does. So basically, the y here is going to get crossed out using one of the consensus theorems. I think it's going to be 19. Yeah, theorem 19. So now we're going to use theorem 19 to basically just cross off this y. So now we've got x or not y or not x. But here we got x or not x essentially, right? X or not x. That is theorem 8. So x or not x is 1. So we can use theorem 8 to say that this is the same as saying 1 or not y, because the x and the not x to get x or not x makes 1. Then 1 or something, that is theorem 6. Something or 1 is just 1. So for us, this is just going to be 1 or something is just 1. And that was theorem 6. So this one, you could call this circuit do everything. Because you get a 1. No matter what your input is, the output is going to be a 1. But I wanted to point out that what happens when you bring more than one variable through an inverter like that. Okay, next I want to work through this problem with you. So what do we have here? This is x. Then we've got y coming in here. So then over here we'll have not y. Right here we've got x. So we're going to have not x over here. Right here we've got y. So we're going to have not y on the other side of the inverter. This is z. Then right here we've got x. So then we've got not x out here. This is y. And this is z. 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 Z's look like this. Okay, now we can start doing some AND gates, right? This AND gate is going to give us x and not y. Then right here we've got z. So this AND gate would give us x and not y and z. Okay, this AND gate gives us not x and not y. So remember, not x and not y don't connect those inverters. So out of this AND gate, we have not x and not y and z. Then moving down here, this AND gate will give us not x and y. This AND gate will give us not x and y and z. Okay, so now we have these OR gates, right? So we've got x and not y and z, or not x and not y and not z. And then when we do this OR gate, it'll be that and this. So all together, or this. So all together, x and not y and z, or not x and not y and z, or not x and y and z. Not x and y and z. Okay, so now we are going to, this is our unsimplified logic expression. Now we're going to use our theorems to simplify it. So we had, I'll write this down on the next slide. X and not y and z, or not x and not y and z, or not x and y and z. Okay, and now we need to use these theorems to simplify that. So the first thing I notice is that the first two terms both have not y and z. So I'm going to use theorem 14 to factor out the common, this is the distributed law, right? You can distribute it through or you can factor it out. So I'm going to use theorem 14 to factor out the yz. So I factor out the not y and z, and I'm left with x or not x, or not x and y and z. Okay, so my x or not x, if we look at theorem 8, x or not x is 1. So this is 1 by using theorem 8. We've got not y and z and 1, or not x and y and z. So anything and 1, that is theorem number 2. Anything and 1 is itself. So I'm going to use theorem 2 to say that this 1 goes away. So now we just got not y and z, or not x and y and z. And now it looks like the only thing I can do is factor out the z. That's theorem 14. So factor out the z, and then we have not y or not x and y. And then if you look inside here, we've got not y and or y, and that's consensus theorem. So this y is going to get knocked off. Not y and y with a not. So not x and x with a not. This is theorem 19 again. So we're going to use theorem 19 to say that this y goes away. So then we've got z time or and not y or not x. And this is in product of sums form. We want it in sum of products. So we need to use theorem 14 to distribute the z. So when we distribute the z, I'll just write it in alphabetical. So not y and z, or not x and z. So we were able to simplify to this, starting from that big old deal. So then the next thing for us to do would be to actually draw this circuit. So I will draw this circuit. We've got 3 variables, x, y, and z. So our first min term here is not y and z. So not y means we need to go through an inverter. And z. And those guys need to go to an AND gate. So let me kind of notate what I'm doing here. This was y. Once you go through the inverter, now it's not y. This is z. So then coming out of here is going to be not y and z. Our other min term is not x and z. So we're going to run x through an inverter so we can have not x and then z. And these guys need to go through an AND gate. So then make little notes here. This was x. So through the inverter, it's not x. This is z. Go through the AND gate. We've got not x and z. And then all we need to do is put an OR gate. Run those 2 puppies into an OR gate. And then the resulting logic expression is exactly what we wanted. It is Y, not Y and Z, or not X and Z. Now, the last thing I want to show you is how to take this and turn it into or put it on Tinkercad. So let me take a little screenshot of this. And I want to build this thing on, oh wait, can you see that? Hang on. Okay, so we want to build this circuit on Tinkercad. I'm going to go to Tinkercad, create a new circuit. All right, so for I need to start with a power supply and a breadboard. Okay, so here is my breadboard. I might just you might need a longer one for the 216, but for this one, this should work. I'm gonna get a power supply. I'm gonna I need AND gates and OR gates. So this is the 08 is a quad AND gate. So this chip has 4 AND gates in it. And then I need some OR gates as well. Here's a quad OR gate. So this chip has 4 OR gates in it. And I'm going to need an inverter too. So I have 2 AND gates, 1 OR gate, and 2 inverters. So I need an inverter gate chip. So inverter. This is a hex inverter. That means it has 6 inverter gates in it. And for the switches, I'll like to use this one. And what I'm going to do is I'm going to run it. I'm going to put the top set of pins in the positive row here and the bottom set of pins in these rows here. So then this can be like my X, my Y, and my Z, and then I just won't use the fourth one. Maybe I'll scoot it over one so that I can run power to here, ground to there. Now remember, all these chips need power and ground run to them. This input is power, that input is ground. So I need to run a wire over to the power for each one of them. And I need to run ground for each one of them. Now my bottom ground row isn't connected to my ground yet, so I need to run a jumper wire from here down to here also. Okay, so now my chips are powered up. or they're wired up. Now I need to look at my schematic here to figure out what to do first. So I need to run through the inverters. Let me see if I can get a little cursor thing going. Through the inverters, I need X going into an inverter and I need Y going into an inverter. So what I'll do is I'll say, so 1 will be X, 2 will be Y, 3 will be Z. So my inverter is this one. So if we look at this guy, it has output 1, let's see, input 1, output 1. So if I put something in input 1, if I put like X in here, it'll shoot out not X here. So I need, I will run a jumper across here for X. I'll make all my X stuff orange. So then I need to go from here over to input 1. So I'm going to run a wire from the input 1 row over to the row that I had my X variable, my X switch on. So if whatever signal is coming down here, X will go in input 1 and come out here, not X. So then if we look at our drawing again, we've done this part right here. We ran X through an inverter and now we have not X. That not X needs to go into an AND input with a Z. So the next thing I want to do is I want to take my output that was coming out of my inverter and take it to an AND input. So this is my output that's giving me my not X, and I need to go into my AND input. So I'll put it in input 1A. That's output 1. So now I've got X going through an inverter. So now I have not X. Not X is going into input 1A of my AND chip. So I want to actually, if I can, make notes on this. So my X, let's see, change my bit. This was, let's see, this was input 1, output 1. Let's see. So this right here, this has input. I can't write little, dang it. This is input and output 1 on the inverter chip. And this is going to input, which input was it that we're going into? We're going into input 1A. So here is, that's 1A. So this is going to be 1B. And then this is going to be output 1 for the AND chip. So going in input 1B in that chip, I need that to be Z. So going into input 1B here, I need Z. So I'm going to run a wire. We'll make it green. And this needs to go to the row that has Z, which is our 3, right? So I need to run a jumper over here, and then this carries Z into output 1B. And so coming out of output 1, we have our not X and Z. So now let's go and put the Y through the inverter. So I need to run a wire from Y over to an inverter input. And I have inputs up here as well. So I might want to take go use input 6. That's what I'll do. So I'm going to use input 6 for this inverter. So here is inverter input 6, and I need to go over to Y. I'll make that yellow. So now I have Y going into input 6, so coming out of input 6 will be not Y. And where does the not Y need to go? The not Y just needs to go into an AND input. That'll get ANDed with a Z. So we just need to take our output 6 to an input in our AND gate. Let's see, here's an input 4B. So I'm going to make a note of what input I put that on. I put it on input 4B of the AND gate. So this is input 4B, which means this is input 4A. So I need to put a Z in at input 4A. This is output 4. Okay, so I need a Z going into input 4A. Here's input 4A. I need a Z going in there. There, that's connected to Z now. Z was 3. And now I just need to put outputs 1 and 4 to be inputs on my OR gate. So outputs 1 and 4 from the AND chip. So here's output 1, here's output 4, and I need to put them into inputs in this OR gate. So here's like input 1A, input 1B. I would have to put them into the one with the same number. Okay, so here is output 1 from the AND chip, and I'm going to put that into input 1 of the OR gate. So I'm going to make a note that output 1 went to input 1 there. So output 1 from my AND went to input 1A on the OR. So the other input needs to be 1B. And so 1B needs to go to and connect to the output 4 from the AND. So here is input 1B. We need that to connect to output 4. So I'll start a wire from here. And for now, I'm just going to run it over here, and then I'll adjust the wire. I'll have it just run like that. So now we're going from output 4 on the AND over to input 1B on the OR. So we're done. Now just whatever output 1 is our output for this circuit. Output 1 on the OR chip. So then what we would do is we would take from output 1, we would, here's what I'm gonna do. So this is where we wanna hook up our LED, right? So I could just take an LED. And make sure the anode is on, rotate this. So my anode is gonna be coming on the row that has output 1. And then, so that's where my anode is. So my cathode is now on row 25. So I need to run a resistor from 25 over to the negative. So from row 25 over to the negative, and we can just make it 100. See how that goes. Okay, now the logic statement for this one was not y and z or not x and z. So anytime I have z and then not one of those two, I should have a light on. So if I turn on z, oh wait, I need to start my simulation. If I turn on z, I should get a light on. Oops, I got a warning. I need to make my reduce. It says this light could burn out. So if I change my resistance to, let's see if I change it to 150, then I don't get that warning. Okay, so z and not one of those. So if I turn so right now I have z and I have not x, so my light should be on. Right now I have z, but I don't have not x or not y, so my light should be off. So then you'll just check out your circuit, make sure it matches the truth table like that. So hopefully that kind of like going over the entire process will help you remember all the little steps. And